You have to wear this, like
Over behind.
behind, and fit it on your ears. So then that microphone should touch your,
Yes,
and
test.
then here. Can you talk?
Yes, test. 1, 2, 3.
Se escucha.
Is it good?
Yes.
Okay. And
¿Aló? ¿Aló? ¿Se escucha? Sí.
where's the remote? I can advance myself, yeah? Thank you.
Entonces vamos
Yeah. 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 Oops. Is it going to fall off?
Oh, well, you can
Put it the other way.
in the pocket. Like that.
There we go.
There.
That's much better.
Okay, so
How much time do I have?
40 minutes.
40 minutes. I'm going to be much less than that.
Bueno, buenas tardes a todos. Damos inicio a la sesión de la tarde con una charla invitada de Francis Chun, Space Situational Awareness and the Falcon Telescope Network. 40 minutos. Francis, bienvenido. Welcome.
Thank you. As Kathy said, I'm Francis Chun from the United States Air Force Academy, and I want to thank the meeting organizers for inviting me to talk about space situational awareness and the Falcon Telescope Network, which I'm a principal investigator on. This has been approved for public release, so you can do anything you want to do to these slides, send it out to your friends and family. But I have to at least say that the views expressed in this article, book, or presentation are those of me and do not necessarily reflect the official policy or position of the United States Air Force Academy, the Air Force, the Department of Defense, or the United States government. It's all me. Okay. So I thought I'd just show you one slide of the United States Air Force Academy. We are located in the foothills of the Rockies in what we call the Pikes Peak region. And if you're familiar with the Rockies, Pikes Peak is a mountain that is over 14,000 feet. And there's about 56 mountain peaks in the state of Colorado above 14,000. And they're known as 14ers. It's in Colorado Springs at an elevation of 7,258 feet or 2,212 meters. And you can see it there. It's on that's the cadet area. And it's on, the base itself is about 19,000 acres or 76 square kilometers. We have about 4,100 cadets or student body with about 400 plus faculty. And our 4 pillars that we have our cadets trained in is through academics, the military side, of course, athletics, and character and honor. And our purpose is primarily to provide officers for the United States Air Force and now the new, or recently new, United States Space Force. So I thought I would talk about space situational awareness and the difference between it and space domain awareness, which is another term you may hear from time to time. I'll talk about the space catalog, primarily the past growth of the space catalog and the future growth. Then I'll talk about my Center for Space Situational Awareness Research, which I run in the Department of Physics and Meteorology. and then focus on the Falcon Telescope Network and the type of research we do with those small telescopes, primarily on unresolved space object characterization. Okay, so I'm just going to read word for word what space situational awareness is. The requisite foundational, current, and predictive knowledge and characterization of space objects and the operational environment upon which space operations depend, including physical, virtual, information, and human dimensions, as well as all factors, activities, and events of all entities conducting or preparing to conduct space operations. Whew, that's a mouthful. And that is captured in a publication called the Joint Publication 3-14, which probably means nothing to you, but it covers space operations for the Air Force and Space Force, for the Department of Defense. Now, space domain awareness encompasses the effective identification, characterization, and understanding of any factor associated with the space domain that could affect space operations and thereby impact the security, safety, economy, or environment of our nation. And that comes from one of the newly formed space deltas, which has space domain awareness as its primary mission. That's a lot of words and a lot of technical jargon. Probably the way I like to look at it is this. Space situational awareness is what happened. And space domain awareness focuses on, do we need to care about it? Is it a threat to our systems, or is it a non-threat? And that, in a nutshell, is the way I look at space situational awareness compared to space domain awareness. Okay? So early in the space age, in the late 50s, early 60s, there were not a lot of satellites orbiting the Earth. You can count them in probably single digits. Fast forward to March of 2007, there's a lot more. You can see the low Earth orbit regime is a lot more populated. The geosynchronous orbit is also starting to become more populated. And then back when I created this slide about 10 years ago, we projected what it would look like this year. And I have to tell you that there's been a tremendous amount of growth in the low Earth orbit, as well as the geosynchronous belt, but that did not account for SpaceX and the Starlinks and the OneWebs and all of that. So there's a lot more stuff around the orbiting around the Earth. Well, so we have evolved from a few military-only assets to multi-agency, military, civil, and a big commercial component. So one phrase you would hear often is space has become congested, competitive, and contested. Everybody's trying to put everything up into space, primarily for communications, but and navigation and timing. Now, another way of looking at the space catalog is that the United States Space Force maintains the public catalog that anyone in the world can have access to. They track routinely over 30,000 objects. You can see most of them are either rocket bodies or pieces of debris, but there are a significant amount of active payloads now, primarily, again, because of commercial companies. They also track a fair number of analyst objects, as they call it. These are objects that they maintain information on that don't necessarily have an origin that they know of. So they routinely track over 30,000 minus those 17,500 analyst objects, but and these objects are at least 10 centimeter size cubes or size objects or larger. When you start thinking smaller than 10 centimeters, there's hundreds of thousands of objects that are in the space catalog. So back in 1978, Don Kessler and Burton Coeur-Palais from NASA published a paper where they looked at satellite collisions and how that can produce a number of fragments which then can produce more fragmentation, collisions, and essentially result in an exponential increase in the number of objects orbiting the Earth. And this has become known as the Kessler syndrome. There are a few websites that I have found useful over my career, and there's actually more than just these. But spacetrack.org, as I mentioned before, anyone can get access to that, and that's the official United States Space Force catalog of public objects. Celestrak is another good one. It gives you more information about two-line elements, which you heard earlier today. N2YO is another good one. And then Heavens Above, I like to use once in a while for determining past opportunities of different space objects over your site. Okay, so NASA's Orbital Debris Office maintains control of their assets, and they always look at the growth in space objects orbiting the Earth. So you can see that if you look at the beginning of the space age and until the end of last year, there's significant jumps due to events that have happened. So in 2007, there was the Chinese ASAT test, which unfortunately we are living with that, the effects of that for quite a while now. And then in 2009, there was a collision between a working satellite called Iridium and an upper stage rocket body called Cosmos from the Russians. And that one had a low probability of collision, but it turned out to essentially have a high probability of happening. And then over the past few years, we've had a tremendous increase in the number of payloads, again, because of Starlink and OneWeb and all of that. So you can see in the satellite box score on the far right that there's about 30,000 objects being tracked. The US has roughly a little less than half of that. But other countries are definitely picking it up. You know, China is certainly launching more and more assets into space. So that's the past growth. Now, what about the future growth? So NASA has done a number of modeling efforts to project over the next couple of 100 years the growth of the space catalog. And so in red are the LEO satellites, in blue are the mid-Earth orbiting or MEO satellites, and then in green are the GEO satellites. So projecting out to 2210, you can see that the low Earth orbits are exponentially increasing. And this is just due to regular satellite launch pace, which is now kind of obsolete because now we have the commercial companies launching more and more. Now, one thing you can notice too is that there's a cycle in the low Earth orbiting population, and that's due primarily to space weather, the solar cycle. So every 11 years, the sun, through either solar flares or coronal mass ejections, pump a lot of energy into the magnetosphere of the Earth, which creates magnetic storms, which pumps a lot of energy into the ionosphere and the upper atmosphere of the Earth. And it's the expansion of that upper atmosphere due to that increase in energy coming from this, essentially from the space weather effects, that helps, that puts satellites into a higher drag atmosphere, and then they start to decay. So one of the forecasts is that if we can apply defense of what they call post-mission disposal. So when you launch a satellite after the mission is done, especially in low Earth orbit, after the mission is done, you have some residual capacity left over to essentially deorbit your satellite. So if that happens, what you see here is, if you have in red are the regular launches with no post-mission disposal. It just keeps growing. And every subsequent one is 10, 50, 75, and 95% disposal effectiveness. You can control the growth of low Earth orbiting satellites as indicated by the green trace. You can control it so that instead of ending up with 60,000 objects, it's a factor of 3 less. Now, if you combine that post-mission disposal effect with active debris removal, you can even control the growth even more. So this is the green line here, projected out, and in the purple are the regular launches with the post-mission disposal, but removing 2 objects a year for the rest of the lifetime. And you can control that growth to something a little more manageable. But if you remove 5 objects a year instead, and we're talking primarily large objects, like spent rocket bodies, then you can really control the growth over the next 200 years. So there are techniques, or there are things we can do to control the growth of the space catalog just by removing some of the large rocket bodies. Okay, so I run the Center for Space Situation Awareness Research, or CSER as we call it, and our purpose is primarily to provide our cadets with an education and research experience in space situational awareness, using primarily small ground-based optical telescopes, and we call that the Falcon Telescope Network. And why is it called the Falcon Telescope Network? Well, because the Falcon is our mascot at the United States Air Force Academy. It's the fastest bird in speed, and of course, the Air Force loves speed. So we focus primarily on using these small ground-based telescopes for unresolved satellite object characterization. And we try to get them out into the field as well, or to meetings, such as the winter meeting for the American Astronomical Society, where we had 2 cadets give a talk or a poster on their polarization research. And then back in 2022, at the FDI down in Santiago, the air show, there was also the first Chilean Space Summit put on by the Chilean Air Force. And so we had our cadets there, and they were intermingling with some of the Chilean Air Force Academy cadets as well. So we try to get our cadets out into the world, talking about their research and interacting with other scholars. Okay, so on campus at the Air Force Academy, we have 2 telescopes. A 1-meter telescope, which is the largest academic telescope in the state of Colorado. It's on a 4 equatorial mount. It has a CCD camera that we maintain at -100 Celsius and 3 millitorr vacuum. It is a 9,000 multi-sector 9,000 by 9,000 pixel array, and with a pixel scale of 1/3 arc seconds per pixel. So it gives us a field of view of about 52 arc minutes on each side. And then we have a 1/2-meter Falcon telescope in a smaller dome that's on a single 4 equatorial mount. It has a CMOS camera with a 9,500 by 6,400 pixel array. It's a smaller plate scale of about 19.19 arc seconds per pixel, and it has a slightly smaller field of view of 1/2 degree by 1/3 of a degree. So the off-campus telescopes is what we call the Falcon Telescope Network. They were primarily developed for satellite observations, but also for astronomy research and STEM outreach. There are 12 locations around the world. They are identical configurations, identical optical tube assembly, identical cupola or dome, cameras, filter wheels, mounts, weather stations, GPS, all sky imagers. They're all identical. The only difference is the building, whatever our partner collaborators were able to build for us. And on the right, you can see our list of partners. They're pretty much all academic institutions, either two-year colleges or four-year colleges or major research universities. In the US, we have primarily within the state of Colorado, but in Chile, we are working with the Universidad of La Serena. In Australia, the University of New South Wales and University of Western Australia. And then in Germany, the Technical University of Braunschweig. And the coverage we have with the Falcon Telescope Network is in terms of different orbital altitudes like the geosynchronous belt or the low Earth orbiting orbits. Having telescopes both in the northern and southern hemisphere gives us dual coverage from both hemispheres of the same part of the geosynchronous belt. And then with the having a lot of telescopes, say within the state of Colorado, gives us a lot of simultaneous dual coverage of low Earth orbiting satellites. So here's what the telescope observatories look like in Littoral Junior College, Fort Lewis College, Northeastern Junior College, Colorado Mesa College, Farish and Yoder. Those are all in Colorado. And then we have one in Penn State, and two in Australia, one in Germany, and then not last but definitely not least, one in Mamayuka Observatory near the town of Vicuña. And I want to point out my colleague, Professor Nilo, in the back with the University of La Serena, who's been with us from almost the get-go when we first developed and installed the telescope there. And if you have any questions as to his ability to use the telescope and the network and what he was able to use it for, I would talk to Jose about that. But our agreement with the University of La Serena is that they would get 25% of the time on their telescope, but they also have access to the rest of the telescopes as well. And that's the same for all of our other collaborators that were listed. So most of the equipment we bought is at least 10 years old or more. They're commercial off-the-shelf systems because we have export controls that we have to adhere to in the United States. And so they're not major research quality type of equipment. They're not consumer quality either. They're somewhat in the middle. But again, they're getting older and they're failing. And so we're going through a major upgrade of the Falcon telescopes. We're replacing essentially everything except the cupola and the telescopia, the optical tube assembly. Pretty much everything else is being replaced. And so we are going from a gear-driven equatorial mount, German equatorial mount, to a direct drive L500 plane wave. And instead of an equatorial configuration, it's going to be an azimuth elevation configuration. We are going from a CCD camera to the CMOS camera, and then going from a single filter wheel with 9 slots to 2 filter wheels with 10 slots each. So we can have a variety of different filters, the Sloan and Cron-Cousin filters, transmission gratings, polarization filters, both linear and circular, and then neutral density filters. So we can, of course, do single filter measurements, but we can also do a combination of measurements, filter measurements as well. So one area we're looking at is spectral polarimetry, for instance. Because we are going to be in an azimuth elevation configuration for the mount, we have to have a rotator. And so we have an integrated rotator focuser from PlaneWave that will allow us to keep everything, keep the image nice and stable as we track across the sky. As I mentioned, we're adding an all-sky imager, and we're adding in another weather station, weather sensor from Spain, Lunatico Cloud Watcher. Okay. So what type of research do we do with the Falcon Telescope Network? Well, if we were able to gain a resolved image of a satellite, there's a lot we can tell about that satellite, a lot we can characterize that satellite with. And from the characteristics of that resolved image, we can understand or infer different types of missions. But most of what we are looking at, either the satellite is too small, even in a low Earth orbiting, or it's too far away so that they become an unresolved signature. And so we use these small telescopes to essentially exploit the same techniques and parameters that astronomers do as well, looking at the photometric signature, the spectral signature, and the polarization signature of these unresolved satellites. So we are developing an image processing pipeline that will allow us to automatically process our images by applying the noise reduction step first, with biases, darks, and flats, and then putting them through a collection process where we process the photometric images separately from the spectral images and the polarimetry images. And essentially come up with the magnitudes, spectra, and degree of linear polarization, and so forth and so on. Okay, so what does photometry tell us? So one of the things that was mentioned earlier was the color index. So here's an example where we have a large geosynchronous communication satellite called DirecTV-10 that we are observing back in 2013. On the x-axis is the longitudinal phase angle. So it's like the phase angle that was mentioned earlier, but projected down into the equatorial plane. And then on the y-axis is the absolute magnitude. So you can see the color index from one part of the wing of the photometric signature to the main glint changes as a function of the solar phase angle, the longitudinal phase angle. So something, whatever the surface is that is producing this reflectance, it's becoming bluer as we go into more favorable phase angle conditions. So that implies that the solar panels may be the surface, the source of the bluing of the signature. But the problem is that we never got simultaneous filter measurements. We always had to rotate between filter to filter. So that threw in some ambiguity into our measurements as to whether or not is indeed simultaneous color measurements coming from the solar panel. So that drove us to look at using transmission gratings and applying a technique called slitless spectroscopy, where we essentially get the entire field of view diffracting through a transmission grating and projecting that spectra onto the image. So the good thing about using transmission gratings is we don't have to worry about having very precise tracking and guiding of the source through a slit. We are getting everything. And this is what some of the images look like. So on the left, we have two satellites, Wild Blue 1 and Anik F2. Those are geostationary satellites, communication satellites, very large, with very long solar panel arrays. And on the right, we have Spaceway 1, DirecTV-10, and DirecTV-12, also large communication satellites. Now, you can also see, so you see the zero order and the first order of the satellite, but you also have the star trails coming through, both the zero order and the first order drift. Now, so sometimes they can cross through our satellite spectra, and so this is a case where we really don't like the stars. We want to try to get a nice pristine image where we don't have to worry about stars. They're contaminating our images just like our satellites are contaminating your images. Okay, so what can we say, what can this slitless spectroscopy signal tell us? So what we have on the left is a plot of wild blue 1, and on the right, a plot of DirecTV 12. On the x-axis from left to right is wavelength, and then on the y-axis is time in seconds from the first image. And then the z-axis is the flux as we call it, or the counts per second. So one thing immediately that comes into mind that you can say is there's a strong glint in wild blue 1 from about 2,500 seconds to 3,000 seconds, and DirecTV 12 has 2 glints. So one thing you can say about the difference between those 2 satellites is that wild blue 1 has solar panels that are essentially aligned with one another, whereas DirecTV 12 has one solar panel canted to the east, the other one canted to the west. Or one is aligned to the 0 degrees, but the other one is not. So in essence, you have 2 solar panels that are not co-aligned to each other. And satellite owner-operators do that primarily for a couple of reasons. One is for power management, especially early in the life of the satellite. And then another is to reduce the torque on the solar panel wings from the solar radiation pressure. Okay, so that's one immediate thing you can say. Wild blue 1 has 1 glint, and DirecTV 12 has 2 glints. The other thing you can see is that if you follow the black vertical trace, notice what happens when you go through a glint. That black trace is essentially the wavelength for the peak in the spectra. And the spectra is, of course, going from left to right. So the peak in the spectra as you're glinting off the solar panels is becoming bluer. And that kind of makes sense because solar panels want to absorb the photons, and most of the photons are on the right side of the black body curve. And most of the older solar panels do not absorb blue photons as well as the red longer photons. So they look bluish. If you've ever seen a solar panel, it looks blue. Now, more modern technology solar panels are able to absorb photons across the spectrum, so they look more black. So both solar panels are reflecting primarily in the blue. The satellite spectrum becomes bluer. So that was definitive proof that the solar panels were the source of the main glint, because that was simultaneous color that we were collecting. Now, the other thing to point out is that there were microglints occurring, as indicated by variation in the black trace. Microglints occurring during the solar panel glint and in between the solar panel glint. And that's what drove us to look at the polarization signature of these satellites. But before we do that, let's kind of focus a little bit more on that double glint from DirecTV 12. So we have 3 baselines. The first baseline is associated with the max flux of the spectra before and after the 2 main glints. And then during the glint, we have another baseline, which drives everything, the spectra, to the blue side. And then in between the 2 glints, we have another baseline coming from a different part of the spacecraft. And the question is, what is that different part of the spacecraft? So that's what drove us to looking at the polarization signature, as I mentioned before. So here on the left, we have a plot of the polarization signature for DirecTV 10, and then on the right for another satellite, DirecTV 15. And on the x-axis is the longitudinal phase angle again. And then on the vertical left axis is the total intensity, or the S0, the first Stokes parameter in the polarization signature. And then in the right, in the red data points, are the degree of linear polarization, or DOLP. So one thing you can see already is that as the satellite starts to glint, as we approach minimum phase angle, there's microglints occurring on the very top of that satellite solar panel glint. And we can see that also occurring in the polarization signature as well. So we're getting polarization glints. However, if you look at DirecTV 15, we have the solar panel glints occurring here and here. There are no microglints associated with that at all. And there's no polarization glints associated with that solar panel glint. And that makes sense because the solar panels are fairly uniform. So as you cross over that normal of the solar panels, you're not moving from any different surface feature from one side to the other side. It's a nice smooth transition. Where you are getting these microglints and the polarization glints are from the spacecraft bus, the payload configuration. So you're getting it from the antennas, the dishes, and all of those other things that help to create the polarization. And we just happen to see it at the same time for a single glint. And these polarization glints, the profile of these glints are fairly stable because the satellite owner-operator are not going to be changing their payload configuration drastically from one day to the next. So whatever signal we get with the polarization glints from DirecTV 15 is going to be stable throughout the year. And so that's one way to characterize or to discriminate between one satellite and another satellite, looking at the polarization glints. Okay, so in summary, I talked about the difference between space situational awareness and space domain awareness, looked at the past growth and future growth of the space catalog, talked about my research center, Center for Space Situational Awareness, and the use of the Falcon Telescope Network for unresolved space object characterization using techniques that the astronomy community has perfected over the years. And with that, I'm happy to take any questions. Now there has to be at least one question.
Okay, thank you, Francis. So let us take questions. Any questions? I happen to have one, and then I'll go to Elvis. I was just wondering the growth in the number of geosatellites. I mean, it's growing slowly, but it's still growing.
Yes.
And in my mind, there is a quite limited space in the geo ring to have satellites. So are those like the garbage that is right away from the geo? Are those working geosatellites, or those are working plus the ones that are dead and still around?
In terms of some of the images?
Yes, you had a plot of the growing number of different, the geo,
right.
The medium, and the...
They're everything, right. So
okay.
there is a disposal orbit for geosynchronous satellites. It's typically about 300 kilometers above the geo belt. So it's super sync. But that post-mission requirement was not in place in the early days of launching satellites into the geostationary orbits.
From the data detect of different objects, it's possible to determine area to mass radio, for example?
To determine?
Yes, the physical property for this object, area to mass radio. What difficulties?
I'm sorry.
Area to mass radio.
Area to mass radio.
Yes, but most of the area to mass, most of the objects we're looking at are operational satellites, and especially in the geostationary belt. There are area to debris objects, what's called hammers, high area to mass ratio objects that can be tracked, but they undergo a lot more orbital dynamics because of their high area to mass ratio. you know, they're like sheets of mylar or something like that that get shredded from a geosynchronous satellite.
In one of your first slides, you talked about 3 types of objects, and I didn't understand what the third one was. Could you go back to one of your initial slides?
Ah, got it.
Okay. To go back.
It's not working. This one, yeah?
Yeah, it should go. Yes.
Yeah.
Pointed.
Nope. Can you escape and go back? Okay.
Yeah, if you,
Okay.
yeah, right here, these analyst objects.
These
Can you-
analyst objects?
Yeah, what are those?
Those are objects that are not attributed to any particular country or origin. Everything in the space catalog is associated with with a country who launched it. Not necessarily with the owner of the payloads, but the country who launched that satellite, which in the early days of the space age made sense because, you know, US was only going to launch their own, Soviet Union the same. But now we have commercial launches, and you know, with SpaceX, they're launching stuff from everybody. China will take anybody's satellite as well. They'll take ours and launch it for us if we paid them. Same with Russia and the European Union as well.
But so those you don't know who launched them, but they are artificial satellites, right? Or-
Yes, but they're easily detectable, and their orbits are maintained by the Space Force. Did that answer your question?
Not really. So what do you think they are?
Well, what do I think they are? Well, they're not UFOs.
No. Well,
That I can
strictly
know.
speaking, they are. If we don't know what they are, but
Well, that's true. Some of them could be debris objects that have not been definitively associated with an event. Some of them could be, I really don't know, quite honestly.
Hello. Well, from a naive point of view, we see that the number of objects is growing and fast. And do you think in any point any new object will represent a threat to security? And if you do think it will represent a threat, when do you think it's going to happen?
When is a very hard question. I don't know when. In terms of low Earth orbits, the solution to controlling that orbital regime is to remove some large objects. I mean, you basically have, whenever you have a large on large collision, you're going to create a lot of debris. And so if you can remove those 5 objects per year, you can control the low Earth orbit. The problem, though, is in the geosynchronous belt. As it was mentioned, it's prime real estate up there. And not just in terms of orbital slots, but also in terms of frequencies, communication frequencies. And so you have to be concerned about satellites, geosynchronous satellites, encroaching on other geosynchronous satellites and kind of sniffing out the communications. Yeah.
Hello, a nice presentation.
Thank you.
I was wondering, the projection that you show about the number of increasing objects that we expect in the future, that one, when do you consider we should start worrying about the Kessler syndrome? I mean, to see that the probability would be very high enough to get more collision than expected.
Yeah, one of the very first meetings of the community, and it's satellite owner-operator community primarily, so like NASA, the Air Force, Department of Defense, was back in about a few years after the Chinese ASAT test in 2007. And that's when it first started to be discussed, looking at active debris removal technology.
And a second quick question is, I saw that the methodology you use using photometry and also spectra and so on to characterize the object you're observing. What about of the kind of debris, for example, boosters, where the shape is elongated or cylindrical? What about those objects with different geometry?
Yeah, we just recently, we were working with a colleague at Leo Labs, if you've ever heard of that private company. One of the experts in space debris is a colleague of mine who used to teach at the Air Force Academy with us, Darren McKnight. He wrote a book on space debris back in the late 80s. And so we were participating in a study with him, as well as with a few other universities in Europe and in the US, where we were collecting light curves of different rocket bodies in low Earth orbits. And these different rocket bodies had different length to diameter ratios. And so we were looking at collecting on different LTD ratio rocket bodies to see whether or not the low LTD ratios were more chaotic in their spin states compared to the longer cylindrical rocket bodies, because they would act more and more like a gravity gradient boom.
Thank you so much.
Question?
Thank you, Francis. That was impressive. Back to the telescopes, your monitoring telescopes. How much did you lose in terms of, say, limiting magnitude in doing field spectroscopy? Because I see you went to larger telescopes, like 50 centimeters, if I understand.
So one of our older telescopes that we did a lot of proof of principle collections was a 0.4 meter telescope. The Falcons, we did go to a 0.5 meter, but all the Falcons are 0.5 meter size telescopes. The only other different telescope we have is that 1 meter on the campus, that 1 meter. So limiting magnitude, as you were talking about.
Yeah, I mean, are you monitoring the same sample as before when you do, or you have to limit to brighter?
Yes. So one of my contractors, my senior scientist, he's leading the study on the limiting magnitudes of each of these different telescopes, the 1 meter and all the other Falcon telescopes. So we are starting to look at that. And we will periodically, over the years, readdress the limiting magnitude and see how that changes as the telescope gets dirtier and dirtier.
Other question?
Okay.
Let us thank Francis again.
Thank you. I gotta get this out. I got deep pockets. Here, let's take this off.
There you go.
Thank you.
Thanks. Okay, so then this.
Yeah, okay.
And on your in.
Yeah. Okay. It's okay.
So now we
You hear
have.
me? Yeah.
Can you hear him?
You hear me?
Yes.
Okay. Yeah.
So now we can have our next talk, David Darson.
Yeah, David Darson. Yeah.
Okay.
Okay. First of all, a big thanks to all people of the organization committee of this nice meeting and workshop. So my speech will be a little bit special because I will not speak directly about astrometry. Indeed, I'm going to tell you about a new camera that can be, this camera can be very useful for astrometry measurements. In fact, I will speak about, I will present a new camera. This camera, Sirius camera, it's a near infrared, shortwave infrared SWIR camera that we entirely developed in my laboratory, LPENS, from ENS Paris. So LPENS, quickly, LPENS is a physics laboratory of ENS Paris. And in this laboratory, we study essentially fundamental physics with theoretical and experimental activities that cover a vast field of all physics domain. And we also developed our own instrumentation and also imaging system like infrared system. So let's go to this camera and its main features. This camera was developed around infrared detector. In fact, it's a classical and hybridized detector from in-gas layer sensitive of infrared, hybridized on classical CMOS readout integrated circuits. This circuit was developed by a French society, New Imaging Technology, NIT, and it's a VGA format with a sensitivity from 0.9 to 1.7 micrometers of wavelength with a very high QE, up to 80%. It's deeply cooled by a vibration-free cryocooler from ambient temperature to 70 Kelvin with a very low dark signal at a lower temperature and real noise lower than 5 electrons with the use of non-destructive readouts. We have we have a very special response mode into the pixel with this camera. We have a first mode, and I'll talk about later, with a linear and logarithmic response on the same image, on the same exposure, and or very classical, and we can switch the pixel response to a classical response with a full linear response in the CTIA. We can do true region of interest on chip, and we reach, for the frame rate, 200 frames per second on the full frame, and up to a few tenths of 10 kilo frames per second with a little region of interest. So now this camera is industrialized and commercialized by a French society like TID, and we can see this camera installed on the T1 meter telescope, and we'll talk about later on this speech. So let's go on the first very special response mode into the pixel. We can turn the pixel response into a photovoltaic mode. In fact, each pixel is a photodiode in photovoltaic mode. So at the very beginning of an exposure, we can have a linear response with the capacitance, with the junction capacitance of the photodiode. And when this capacitance is saturated, we have above the linear response, the saturation of each linear response, we have a logarithmic response that is a response in a real time of the incident photon flux on the pixels. And it's a logarithmic response. So you can see here a classical image. It doesn't really work. Yes, it's difficult. A classical image in infrared with this response mode, with the light bulb with a logarithmic response in a logarithmic compression mode, and on the background behind low signal in a linear mode. Here again, strange results, very special results with a diffraction, with a laser diffraction, and it's just one picture. And you can count all the diffraction rings around the first ring, and we can count up to 55 rings on the same image with a logarithmic response in the middle here, and the transition to the linear response here. So now, I don't know if the video works. If it doesn't work, it doesn't matter. Okay. Because there is two videos, okay, it doesn't matter. Ça marche? Non, ça marche pas. Click? Click, no. No, no. Okay, so. Sous le bouton dessus? No. Okay. Okay, it doesn't matter. Maybe later I can show you on my laptop. But in fact, we can use non-destructive readout in the same time with this kind of response. With non-destructive readout, we are able to see the evolution of the signal during an exposure without destruction of the signal. So we can follow the evolution of the signal during the exposure, and for the brighter area here, at the beginning of the exposure, you have the transition to the logarithmic response. So in this brighter area, you have an instant, you have a real-time response in the logarithmic response of the, it depends on the incident photon flux, photon light. So you can see with the non-destructive readout, you can follow the movement in real time here of Saturn with the turbulence. But around, you are still in the linear part, and you can follow here the accumulation in this linear part, in the same exposure, during the same exposure. So I can show you later on my laptop. So let's go to the first astronomical result. And thanks to a close collaboration with François Collard here, you know him now with the 3-point project, and but he is also the PI of the T1 meter telescope, the 1 meter telescope at the Pic du Midi Observatory on the top of the French Pyrenees. And with this collaboration, we can use and test at any time our camera on these telescopes. So it's a 1 meter telescope with a focal length of 70 meters, and we installed the camera on the Nasmith focal plane here, and with a scale of about 0.80 18 arcseconds per pixel. So here, very quickly, a very classical image in infrared of Jupiter, but with a classical stack of short exposure. So it's very classical, like all other camera. Here again, but in different wavelengths. But let's go. So the video works here. But yes, this one works. Okay. But here we have a very special, another very special readout mode with this camera, only in linear response, and we use only non-descriptive readouts in linear, full linear response, and during an exposure, we can reach a very high dynamic using this non-destructive readout, and also we can reduce all the noise, readout noise, and photon noise during an exposure when we use these non-destructive readouts. So we have, at the end of the exposure, we have an image with a huge, very huge dynamics. And to see this image on our screen with just 256 grade levels, I had to stretch a lot histogram and to apply gradient to remove or plane the background. But, and if you don't see, I believe me, and I can show you on my laptop, but here, on this image, you can see, so Jupiter, okay, it's very classical, but near Jupiter, you can see Metis and TB, very small object, very small satellite, near Jupiter on the same image. And it is the first time that we can see all these objects around the bright object on the same image. The difference in magnitude is huge, of course, because Jupiter is about -3, and Metis is about 17.5 of magnitude. And also, Metis is completely on a very high background because he is Metis is in the diffusion photon flow around Jupiter. Diffusion, atmospheric diffusion, optical diffusion, but the background around Jupiter is very high. I remove this background by when I apply a gradient here, but Metis is in very high background. But with, and thanks to the non-destructive readout, I can remove photon noise and readout noise, and I can see very low contrast in a very high background. So, no, sorry. Very quickly, because I have no time here, Saturn in linear and logarithmic mode. So you can see Saturn here in the logarithmic response, and behind Saturn, you can see a lot of very faint objects. Another result with Saturn, but here in a full linear mode, and for the first time on the same image, you can see Saturn, and with some details on Saturn, and also Calypso and Helen, just near of Saturn. Here is just a use of non-destructive readout to remove readout noise, and you can see the efficiency of this process. I go quickly, and we can speak a lot of later. Here another result, great result. We saw the ring around Uranus on the same image. And just before conclude, I don't know if you see well these images, but here, for the very first time, we can see in the same time the bright side of Venus and the dark side of Venus, with the black body, the radiation of the black body through the cloud of Venus, but also in the limb here of Venus, there are brighter areas, and these brighter areas are in fact the night glowing in the high atmosphere of Venus. So this is the first time we can see in the same time these two parts of Venus. And the very new image was taken in February of this year. So yes, we filmed 2 patterns with this camera before its industrialization. And okay, so to conclude, if you have any questions, so yes, I think this camera, and we think that this camera can be very useful for astrometry and to detect and to follow and to survey little and very faint objects around a very bright one. Okay.
Questions?
Thank you very much. Two questions.
Mm-hmm.
You went very fast at the end, but what is that of adaptive optics that you show at the end? The adaptive optics that you show at the end, what was that?
Okay, yeah. Okay. In fact, it's a shame because the first video don't work. So I go back here. In fact, during an exposure, for example, 1 second of 1 second exposure, we are able to take take 200 non-destructive readouts. And during this exposure, every 5 milliseconds, you have a new images. You follow the signal. And at the beginning of the exposure, with a brightest object like Saturn, there is a transition in the logarithmic response. So at this moment of the exposure, you can follow in real time the movement of Saturn, like the tip tilt. So if you have the information of the tip tilt, you can feed back on a optical in a mirror, a deformable mirror, and you can feedback and you can correct, for example, the tip tilt with the information that you take on Saturn. So for the very weak object around Saturn, you can have a better signal to noise ratio with a corrected image.
Okay.
So you don't need two optical paths, with one path for the detection and one path for the scientific image.
Yeah, I think that will be very interesting for binary stars also. And the second question is, how much does this camera cost?
So, this is the first model, and for this deeply cooled camera, it's about 120 kilo euros.
Okay.
It's about
120,000.
Yeah, 120,000 for this first model.
I want to.
But yes, we developed the Peltier cooled model.
Yeah, it will be cheaper.
Less expensive.
Okay. That's very
Because
nice.
the cryo cooler is very, very expensive.
Can imagine. Thank you.
How big is the sensor?
How big is?
How big is the sensor?
How big is the sensor? Oh, yeah.
Because it looks like a very small field for the moment.
Okay. How big? I think yes. In fact, is 9. It's about 10 millimeters by 8 millimeters.
Okay. So how many photodiodes? How many pixels?
How many pixels?
Where
It's
is
640 per 5. Yeah, here it's a
Where is
VGA. It's a VGA sensor here.
Oh, okay.
Yeah.
Oh, there. Okay.
Yes.
So can you? Are you planning to make them a little bit bigger?
Yeah, yeah. And we are developing now the next generation with a bigger one and 1,000 per 1,200 pixels.
And you're thinking of space, right? Because you don't need the cryo cooler. Because
We
in
don't have the
L2
space
you can reach.
qualification. We don't have for the moment the space qualification. Yeah.
Are you thinking of making a space
Maybe
version?
in the future. Maybe I don't know.
What do you mean the future? That's a lot of business there.
Yeah.
All right. So let's thank David once again.
Okay. Thank you.
And we go to our next talk. So our next speaker, unfortunately, could not attend Adela in person, but he sent us a recording of his talk. So he cannot take questions either, but then at least we will be able to listen to his talk recorded. So let us go for it.
Good afternoon, everyone. I am José Fernández, Associate Professor of the Universidad Católica del Norte. Today I will be talking about graph system. This is a galactic dynamic model for orbit computation and kinematic. I am José Fernández, Associate Professor of the Universidad Católica del Norte. Today I will be talking about graph system. This is a galactic dynamic model for orbit computation and kinematic prediction on the Milky Way galaxy. Okay, I would like to start mentioning that the model is able for everyone. In this website, you can click over there and go immediately to the galactic simulation. So this model constitutes the two main galactic components. The main galactic component, the axisymmetric one. The axisymmetric means the superposition from multiple stellar dips, including the sigma and sig disk components, following the particle density profile. For the sig disk, we follow the inasto profile, and the sig disk component follow the hyperbolic secant. Also, the axisymmetric component include the interstellar matter, the overhead stellar halo, and the dark matter halo. In the inner galaxy, we take into account the gravitational potential perturbation produced by the supermassive black hole. The other important galactic component in the inner galaxy is the no-axisymmetric contribution. The no-axisymmetric contribution means the perturbation produced by the galactic bar. The galactic bar is modeled by the graph system model by the simple correlate ellipsoidal bar. This is the option that is public in the website. So this is also important to mention that this model has produced around to 150 papers in many different components of the galaxy that is implemented. Now I would like to show you the general picture of the website that you can go there to make a simulation prediction of any particular object on the galaxy that you are studying. You just need to register on the website and you will immediately get the password to go inside to the simulation, and the main input parameter that you need to fill inside to this website is the main coordinates, the right ascension, declination, and proper motion, radial velocity, and heliocentric velocity. If you know the error bar for every of these observational parameters, you can include that and get the Monte Carlo simulation for every particular orbit. So what exactly the model do? The model starts from the observational parameter. We input that observational parameter into the code. The code implement or call the density profile. We can activate the different galactic components that I already has mentioned, the axisymmetric component and the no-axisymmetric component. And then with this different combination of the density profile, the model compute the global gravitational potential. With the gravitational potential, the model infer the field force. With the field force, we compute the prediction of the rotation curve, and the rotation curve is constrained by kinematic from observation. Okay, in the end, the model only fixes the stellar parameter for the stellar halo and also the main physical parameter of the galactic disk. This iterates multiple times in order to better constrain from the observational point of view the different stellar components. Okay. When the stellar component is fixed, the model is now able to compute the galactic orbit, the future and past galactic orbit. This is only the prediction of the model, just to show you how well it's reproducing the observation. On the left is the kinematic behavior of the galactic baron component. Is following very well the kinematic trends on the galactic bulge and the kinematic of the bulge. So the velocity dispersion is also fitting very well the observation. So you can adopt for every galactic component, you can see the model is reproducing the galactic field in conclusion. So in the solar position, the model is also fitting very well the observation. So you can see the different model adopting different angle orientation is fitting the observation. So the model implements different pattern speed. You can configure that in the website. Before running the simulation, you can change the pattern speed of the bar. You can change also the mass of the bar and the initial bar angle. So what is new? That what we are incorporating new in the model? We are incorporating the other more complex bar structure inside to the gravitational potential. One of this bar structure is the boxy pin-up bar, following the BBBX profile. In the inner galaxy, we move to the BBBX because this is more deeper than the 2-mass one. And also the second model for the bar is the elliptical one, and the prolate one that's the I have already mentioned. The elliptical and the prolate bar are more faster to compute the orbit. The boxy bar is more complex, take more time to compute the orbit. No? Now we are also implementing inside this potential model the spiral arc contribution. The spiral arc are very realistic structure of the spiral arc on the galactic disk, doing some important dynamical contribution to the galactic potential. If you need to run one of these complex gravitational potential model, you just need to send email to me in order to run any simulation in any of these configuration. No? We will be implementing that in the website very soon, but it's not still able in the public version, but we will be implementing soon. So I would like to explain very quickly the 3 different spiral arc models that the graphic system is adopting. One of these is the Perla one. Here you can see the representation of the model, the pitch angular orientation is in this table is around 216. The density profile decrease for this configuration decrease linearly from the inner galaxy to the outer galaxy. So every spiral arm structure have the constant width. The second version or the second model of the spiral arm is more or less similar to the field one, adopting the constant width for the spiral arm, but the density profile decrease as hyperbolic second from the inner to the outer part of the galaxy. And the third one is a little bit more complex model that increase the width to the outer region of the galaxy. This is the reason that we put some different cycles in the along to the spiral arm, and the density decrease as hyperbolic second square. So to summarize, we have three models. Every model will have important contribution to the dynamical behavior of any object on the galaxy. So this is one example from one particular object on the galaxy, adopting the different configuration of the model. The first one is only the axisymmetric without any bar or spiral contribution. You see the typical orbit in the R and Z plane, and this is the energy as function to the integration time. So you can, for example, see the orbit configuration, the axisymmetry compared now, including the galactic bar perturbation, the orbit change lot the configuration, the orbital configuration. No? Now, including the spiral arm, you can see, for example, the orbit is moving to the high galactic plane now with the inclusion to the spiral arm model. The spiral 2 or spiral 3 model, that you can see the orbit is more coplanar over that. So we see important contribution to the spiral arm and the bar structure to the galactic dynamic or any object on the galaxy. So the grapple model is also able to reproduce the kinematic map in any part of the galaxy. If you are interested only to compare, for example, the kinematic from any particular part of the sky, the model can give to you some kinematic map for different stellar population. So because Graph system is following the same approach like Besançon galaxy model, but in the more realistic way, in particular for the kinematics, because the kinematic is taking into account that kind of contribution, the galactic bar and the spiral arm. So here I just showed two very simple models. The first one is for every stellar population, from the more younger population and the more ordered one. You see the galactic halo. You can see, for example, the distribution of the kinematic map on the galactic bar. The bottom panel means the galactic field. So it's not following the galactic bar structure. This is a different kinematic map for the galactic disk population. The population 9 means the typical kinematic map of kinematic behavior expected by stellar behavior. So now what is next? What is next? And we are still in the good time because it's approaching many large sorbet in the sky, like LSST and Gaia DR4, coming with many radial velocity information, width and form, SULAM-5 million stars. So for all this spectroscopic and photometric survey, we can to inject that information into the code, petabyte information that will be releasing very soon in the next couple of years, and then we can predict billion orbits for the world galaxies and construct the homogeneous kinematic map for every galactic component. So this is important to interpret the data. So the code can give to you physical parameters like kinematics and proper motion, and then we can compare directly with any of these particular photometric spectroscopic survey. So here is just one example that the code has been implemented. The field one on the left is the discovery of chemical anomalous stellar halo. So, studying the apogee spectroscopic survey, we have identified a nitrogen-rich star being ejected from the galaxy. We try to connect that with the global cluster formation scenarios, and the right panel shows you the multiple stellar halo population that has been discovered implemented in the TSNE algorithm. So you can see the talk from Mario Ortigosa that will be talking more detail about these discoveries, implementing GRAPO, combining GRAPO with chemical information from the SLM4. So here is another couple more examples that the GRAPO has been recently used. For example, WERCO have examined many open clusters on the galaxy, finding interesting orbital configuration around to the galactic bar, and SOTO have tracks the M-dwarf star on the galaxy, try to reconstruct the galactic Dixon information, and also Thais and Macarena is studying the bulge global cluster in the inner galaxy. These two particular clusters have new radial velocity information from the Sloan 4. Petralia, combining the Ingris spectra and Weiner's spectra, have tracks the new global cluster in dynamical history. So here this is on the paper that we have already published, but I would like to highlight the Elisa Garro papers. She have discovered several BBBBX new bulge global cluster. So doing the spectroscopic follow-up from this cluster, we can trace for the first time the dynamical history for many of them. So this is all. If you have any question, please just let me know. So I would like to invite you to use the code, to implement the code. If you need something to do or something to run, just type to me one email. We can definitely to implement the code in any of your work that you are developing. No? Thank you very much.
Yes. We thank Jose for his recorded presentation. Sadly, again, and he sent his apologies. But you saw his email, so any of you interested in learning more and using his GrabPod 16 code, email him. Very willing to guide you in using the code. So now we are on a break, right? Just in time. Very good. So let's go have dinner, 1 hour, and then we are back for the final talk of today that will be recorded too. There is a note that I have to say. ¿Algo que tengo que decir? Okay, so those of you who have not registered yet, the ones who arrived late night yesterday that still have to register and have to get your material, we can try to do that now in a few minutes. So let's go have dinner. Sí. La puedes poner.
Good evening, everyone. Thanks Adela Organization Committee's invitation. Let me share.
¿Cómo? Ok. Entonces, ya estamos de vuelta y vamos ahora a escuchar la charla invitada de Jing Liu. Está encendido. Ok, vamos a... sí, lo escucho. Vamos a ver ahorita cómo resolvemos. Pero antes vamos a dar inicio a esta charla invitada. La conferencista desafortunadamente tampoco pudo venir, entonces nos envió su charla grabada. Ahí creo que ya terminó el sonido. Y entonces vamos a escuchar su charla grabada a continuación. Adelante.
Good evening, everyone. Thanks Adela Organization Committee's invitation. Let me have opportunity to share my work with dear colleagues. I'm Liu Jing from National Astronomical Observatory, Chinese Academy of Science. Today my talk will focus on the Yao Light Telescope, briefly named YLT. I'll introduce the near-Earth asteroid-related work of the YLT. This is content of my presentation. First is about background information on near-Earth asteroid. Near-Earth asteroid are celestial bodies whose orbits intersect or come close to Earth's orbit, with a minimum distance less than 0.3 astronomical units. Their orbits are influenced by gravitational perturbation from other celestial bodies in the solar system. This means the threat level they pose to Earth can vary over time. The asteroid including 4 types, according to their orbital relation with the Earth: Apollo, Asen, Amor, and the others. Most of them is Apollo type. Historically, near-Earth asteroids have had significant impacts. I list here. First events happened around 65 million years ago. The 10 to 15 kilometers asteroid hit Chicxulub in Mexico, leading to the extinction of dinosaurs. The second is so-called Tunguska event in 1908, when a 15 to 100 meter size asteroid exploded over in Siberia. It flattened 2,000 square kilometers of forest. Most recently, in 2013, a 17 to 20 meter size asteroid exploded over Chelyabinsk in Russia, and it injured over 1,500 people and causing substantial building damage. And these events bring international concern. The United Nations take a quick action. UN COPIOS established 2 organizations almost in the second month of Chelyabinsk event happened: I1 and SIMPAGE. I1 is International Asteroid Warning Network. It's for observation, analysis, and modeling the asteroid threat. The same page is Space Mission Planning and Advisory Group, which gives the cooperation defense decision among space agencies and countries to prevent damage of asteroid to the Earth and the region and people. Under this framework and cooperation mechanism, several dangerous asteroids have been successfully observed and predicted. (2024) YR4 is a typical example. It was first discovered by the Atlas telescope in Chile on December 2024. This asteroid, its brightness was relatively dim, but through continuous observation and data accumulation, its orbital parameters were determined. The initial observation indicate this asteroid is an S-type asteroid with a diameter between 40 and 90 meters. The impact probability of 2024 YR4 once reached as high as 3%. I1 issued an impact risk notice in January this year, stating that 2024 YR4 might hit the Earth on December 22 in 2032. If it were to actually impact the Earth, the energy it would release would be equivalent to 8 million tons of TNT. However, with the increase of observational data and the refinement of orbital calculations, its impact probability has gradually decreased, and currently it is only 0.004%. So, in February this year, I1 issued a notice of risk removal. NIOC, our institute, has a long history for observation asteroid and analyzation asteroid. During this campaign for 2024 YR4, our institute also contributed observation data. We observed it on January 7th, 2025. Now let's show the Your Light Telescope, YRT. The Your Light Telescope is designed for searching and tracking potentially hazardous asteroids. It can search for near-Earth asteroids with diameter of hundreds of meters and follow up on approaching near-Earth asteroids. It also helps in researching near-Earth asteroid characteristics such as albedo and spin characteristics, improving orbit accuracy, and participating in the International Asteroid Warning Network for joint observation and assessing near-Earth asteroid collision threats. The Your Light Telescope is an ART-S telescope. Its aperture is 1.2 meters, with a field of view of 3 degrees times 3 degrees, and installed by CMOS detectors with a resolution of 6K times 6K. Your Light Telescope was proposed and augmented in 2017 It was approved in 2019. In the following 2 years, the telescope was produced and the site was constructed. In 2021, the telescope was installed and achieved its first light. After that, the telescope took 2 years for trial operation, and in 2024, the telescope was put into operation. The Yale Light Telescope is located in Ali, Tibet, which is in the southwest of China. The site is at the top of the mountain with an altitude of 5,400 meters. The site conditions are quite favorable, with clear nights of around 300 days, seeing conditions of less than 0.9 accidents, sky brightness of around 22 magnitude, and with good atmospheric transmittance. This site was selected from about 20 years ago. The data showed that it's one of the best observatory sites in the world. And during these years, the road and the communication and the electricity condition to the top of the mountain have been gradually constructed. As to your light telescope limiting magnitude, in short explorer time mode, its limiting magnitude is about 18, and in long explorer time mode, the magnitude can reach to 21.2, and in synthetic tracking mode, the limiting magnitude can go up to 23 magnitude. Now let's move to look at VLT's observation strategy and its data processing procedure. VLT has 2 observation modes. Survey mode design focuses on regions with high NEA probabilities, such as ecliptic plane and areas near Earth orbit, to maximize detection efficiency. It can survey 1,400 square degrees to a depth of magnitude 21 every night and cover the whole sky once within 20 days. In tracking mode, VLT gathers photometric data to determine the brightness of NEAs, providing clues about their composition and surface properties. It also takes astrometric measurements to precisely determine the position and rotation of NEAs, enabling accurate orbit determination and predict their future trajectories. The VLT works closely with global NEA observation networks, such as International Asteroid Warning Network and the Minor Planet Center, to share data and coordinate observations. VLT data processing include image processing and orbital determination and impact risk analysis. Image process pipeline handles vast amounts of observation data to identify asteroids. Artificial intelligence algorithms are employed to classify detected objects, improving detection accuracy and efficiency. For orbit determination, telescopic observations are used to check positions. By measuring angles and timing, numerical methods are applied to compute trajectories. The weightless square root estimation refines the orbit, accounting for gravitational perturbation from planets. Impact risk analysis assesses trajectories, size, and velocity using observations and simulations. The probability of collision, potential damage, and mitigation options are evaluated. considering uncertainties. In the aspect of NA imaging processing, we proposed a moving target detection method that uses machine learning to identify color sequences. This method mainly includes steps such as image pre-processing, image alignment, image coloring, and object detection based on YOLO. Preliminary results show that this method is effective and fast. We have developed 3 different impact risk assessment methods, which can basically cover all application scenarios. The linear model is simple and rough, but it has a fast calculation speed. The LOV model has high accuracy and a relatively fast speed. The Monte Carlo model has the highest accuracy, but its computational efficiency is low. Let's show some observation experiment results. Since September 2021, VLT telescope has carried out precise measurements on several NEAs that flew past the Earth to improve their orbit and characteristics. On September 20, 2021, the experimental result of the 2021 QV6 was acquired. The Near-Earth asteroid 2021 QV6 is an Apollo-type asteroid with a diameter of about 60 to 100 meters. It was discovered by Pan-STARRS telescope on August 31, 2021. We observed it on the evening of September 20, 2021. The image shows here the superposition of 5 frames with an exposure time of 5 seconds taken. The apparent magnitude is about 17.3. In November 2023, VLT has carried out precise tracking on several NEAs for its MPC code application. The result shows it has very high precision. Since December 2023, the self-developed asteroid survey software has been continuously used to guide the VLT to conduct sky surveys, obtaining a large amount of observation data on asteroid. In 2024, the VLT was officially assigned the MPC code N57. The VLT has also conducted observation of 2016 H03, the near-Earth asteroid that will be flyby explored in China's upcoming Tianwen-2 Mars exploration mission. Due to its visual magnitude being dimmer than 22.5 magnitude, it's difficult to detect for many telescopes. However, the VLT was able to effectively extract the object from the image synthesized using 20 images with an exposure time of 30 seconds on March 2nd, 2025. During sky survey observations, the VLT has discovered some asteroid. For instance, on the night of May 16, 2024, the VLT observed and processed a suspected asteroid, providing valuable data for further analysis. Last is conclusion and future outlook. The VRT has made contributions to NEA observations through its wide-field capabilities, advanced data processing systems, and collaborative effort with the global astronomical community. The VRT has refined the orbits of non-NEAs and provides valuable data for scientific research, enhancing understanding of this object and their potential threats. The VRT's achievement highlights the importance of continued investment in NEA observation facilities and technologies to ensure the safety and well-being of our planet. The future of near-Earth asteroid observations with the VRT telescope looks promising, with ongoing upgrades and enhancement planned to further improve its capabilities and expand its contributions to astronomical research. Continued international collaboration and integration with other observatories will be crucial for advancing our knowledge of near-Earth asteroids and developing effective structures to mitigate potential threats. That's my presentation. Thank you for your attention.
So we thank Ying Liu for her presentation. And now we are actually a bit ahead of the schedule, which is great. Now, a few short announcements, and the people who is in the organization, just let me know if I'm missing something. For those that have talks tomorrow, aquellos que tienen charlas mañana, please upload the talks on the Google Drive that we instructed. Por favor, carguen sus charlas. Los que tienen charlas mañana, por favor, súbalas al Google Drive. ¿Qué más anuncios tenemos? Las personas que no se han inscrito, people who has not registered yet, please come to me now. You have to fill in quite a few forms. Tienen que llenar unas cuantas formas todavía y además entregarles el material, nuestras lindas bolsas de la región de Atacama. Había olvidado mencionarlo, si alguno de ustedes tiene alguna pequeña dolencia médica que necesita algún analgésico, alguna cosa leve, porque no tenemos nada muy avanzado, nuestro medical officer y Mr. Simpatía pueden consultar con él si necesitan algún medicamento ligero. No. Finalmente, ¿qué otra cosa tenemos pendiente? Ok, entonces vamos a aprovechar entonces esta sesión que ya va a ser un poco extendida y nosotros tenemos ahora una parte de presentación de pósters. La mecánica es la siguiente. Quienes presentan póster, y si quieren vayan haciendo la fila los que quieren venir, se van a presentar aquí 2 minutos, máximo tope, y van a hablar de su póster que está en la sala contigua. Entonces, por ejemplo, yo soy Caterine Vieira, vengo del Instituto de Astronomía y Ciencias Planetarias de la Universidad de Atacama y tengo un póster que trata sobre los lindos cielos azules de la región. Hemos trabajado con datos de determinados observatorios y hemos concluido que este es el mejor lugar del mundo para observar el cielo. Muchas gracias. ¿Verdad? Esa es la presentación que queremos para que den a conocer su trabajo y después en los coffee breaks pues ya tengan visitantes. ¿Comenzamos? Entonces vamos a hacer quizás acá primero un grupo. Vamos a hacer un grupo aquí para que no haya tanto... Y bueno, técnicamente tenemos media hora, así que 15. 15. Veo más de 15. 2, 4, 6, 8, 10, 12, 14, 15. Hasta tú que me miras a mí, tú eres el último. 15 aquí. A ver de nuevo. 2, 4, 6, 8, 10, 12, 14. Lentes 15. Hasta ahí. Hay varios de lentes. Bueno, de todas maneras, si nos da el tiempo, pues vamos a proceder. Ahorita son las 20:30, en realidad estamos bastante adelantados, así que probablemente nos va a dar chance para todos. Que comience el evento.
Hi, my name is Carolina Rojas. I am PhD student of the Instituto de Astronomía de la Universidad Nacional Autónoma de México. And I have a poster about my project thesis, and it's called High Resolution Follow-up Observational Program for stars within 18 parsecs from the solar neighborhood. And it's like a survey of all stars within this distance, limited only by volume, and for that reason we have observation in the north hemisphere, and the southern hemisphere in the north, in the San Pedro Mártir, en el Observatorio Astronómico Nacional de San Pedro Mártir, and in the south in La Silla Observatory with the NTT telescope, and thank you.
Well, hi everyone. My name is Bolivia. I'm a postdoc at Benemérita Universidad Autónoma de Puebla, which is in Mexico. That's a very long name for a university. And I have a beautiful purple poster that you will see there. And the poster is mainly presenting a code that I have developed during these years, which is intended to characterize the structures of samples of star clusters, which are very interesting and very helpful to try to understand, for instance, how globular clusters form, because the idea is that in this poster, I'm presenting mostly the work on superstar clusters, which are like protoglobular clusters. And the other result is that with this code, I'm presenting in the context of the dynamical evolution of star clusters some of the results we are planning to have when the LSST sees its first light by a Rubin telescope. And please go to see my poster. I'll be there to try to answer to all the questions you have. And I'll be presenting some of the results. Sorry, this is kind of long. Okay, so I'll be also trying to present the contribution of the Mexican LSST MX group. Thank you so much.
Hola, buenas noches a todos. Mi nombre es Daniel Rodríguez, soy de la Universidad Central de Venezuela. Me gradué recientemente de física y bueno, trabajé con Iván Cabrera y Gladys Magris del SIDA en un trabajo donde estudiamos evolución y formación de galaxias. Lo que hicimos fue utilizar cúmulos globulares para hacer un trazado de la evolución química de las galaxias. ¿Qué hicimos? Agarramos la espectroscopía de los cúmulos y la fotometría y buscamos una manera de combinar los dos. Esto funcionó relativamente bien para los cúmulos más viejos, donde esperábamos resolver el problema de la degeneración de la metalicidad. Sin embargo, conseguimos que para los cúmulos más jóvenes el método no estaba funcionando bien. Por lo tanto, tenemos que seguir trabajando en el problema. Y bueno, pueden ver el póster y si tienen ideas también soy libre de aceptarlas. Bien, gracias.
Hello everyone, I'm a first-year master's student at the Universidad de Valparaíso, and I work with eclipsing binaries. Sorry. My name is Pablo Fernandez. That's not important. And my poster is about a binary system with ETVs, that's eclipsing time variations, where the primary eclipse of the system comes with a delay. So we're trying to figure out why, trying different models, and hopefully my proposal that I sent today gets accepted to find the answer. You can read more about it on my poster.
Hi everyone, Can you hear me well? Yes, okay. Hi everyone, my name is Javier Cabello. I am a master's student at Universidad de Concepción. So in my project, I am performing numerical simulations in order to explain and modeling the luminous component of dwarf spheroidal galaxies. In this case, we choose as a template the ultra-faint dwarf Ursa Major 2. In our models, we model the disorbiting star cluster model in which stars are orbiting the central part of an invisible dark matter halo, spreading as the form of associations or star clusters. And after 2 gigayears, we get a luminous component very similar to the ultra-faint population around our Milky Way, and our models are able to reproduce the kinematic and structural properties of dwarf spheroidal galaxies like Ursa Major 2. And in the main result of the simulations regard the saving of a lot of CPU time, because we don't need to follow the dynamical evolution of the ultra-faint galaxy until 12 gigayears. That is the age of the stellar population in these galaxies. So our simulations evolved into a typical ultra-faint galaxy within 2 gigayears. So this is the main result. Thank you.
Hello, my name is Leonardo País, postdoc from the National University of La Plata, Argentina. Well, my paper, my poster talks about detection of open clusters and associations using clustering algorithm HDV-scan and Gaia DR3 data, where we find or detect 24 open clusters and 3 stellar associations. We study the direction of Cygnus OB2 association. And well, in my poster is all the information that if you want to read it, you're welcome for that. Thank you very much.
Buenas noches, mi nombre es Joana Quinteros, vengo del Observatorio Astronómico Félix Aguilar de San Juan, Argentina. Vengo con trampa porque voy a hablar de 3 pósters. 2 son míos y el tercero es de un compañero que no pudo venir, de Ricardo Podestá. Los 2 míos, que los invito a ver, es sobre la estación Doris de San Juan y sus resultados sobre el movimiento del polo. Y el otro es sobre la determinación de los vectores de colocalización en el observatorio. Y el de mi compañero es sobre la determinación de la deflexión de la vertical, los métodos que se han utilizado para la medición en el sitio CART. Así que bueno, los invito. Creo que estuvo muy bien el tiempo.
Hola, buenas noches. Soy Sebastián Espinosa. Bueno, de partida yo no soy astrónomo, soy ingeniero eléctrico, así que soy un infiltrado acá. Pero igual les quiero mostrar mi trabajo, que es un póster relacionado con un enfoque más matemático, más estadístico de los modelos astrométricos y fotométricos que ocupan ustedes actualmente. La idea es que nosotros hacemos un análisis un poquito más teórico y queremos entender el comportamiento estadístico de los estimadores que ustedes ocupan para poder, por ejemplo, estimar la posición o calcular el flujo de una fuente puntual, llámese una estrella, etc. Es un trabajo que en realidad abarca muchos años, que ha sido liderado junto con el profesor René Méndez y otros profesores también del área estadística, matemática, eléctrica y junto conmigo. Y la verdad es que han sido hartos papers que lo íbamos recopilando en un gran survey que estamos trabajando ahora, y los invito a que ustedes vean la evolución de todos estos trabajos, en particular si les gustan mucho las ecuaciones matemáticas y resultados, teoremas que les ayude a demostrar, por ejemplo, el desempeño de distintos estimadores, tal sea como el mínimos cuadrados, máxima verosimilitud, en estos contextos que son bien clásicos, pero creo que pueden ser muy útiles para los trabajos que están haciendo también ustedes. Muchas gracias.
Well, my name is Josephine Chamon. I am third year student of the PhD in Universidad Antofagasta. My poster is about my master project thesis, and in this investigation we develop an instrument to measure the brightness reflectivity of materials commonly using in the LEO satellites. And with this brightness data, we apply 3 different mathematical models, and then each model was compared with the observational data of the LEO satellites, in particular with the starling population, right? This investigation have a 3 branch of investigation. In first place, we have the instrumental develop, then we have the data analyze, and finally, I also have a social branch because I study the social perception of this type of satellite in the community. This.
Hi everyone, my name is Steven Alfonso. I'm a PhD from Universidad de los Andes in Bogotá, Colombia. I think the microphone is not working. Is it working? Okay. My poster is about simulation-based inference for binary stars, which is a methodology to estimate masses for binary stars based just on photometry. This is part of a work that I've been working with Professor Katy Vieira and my advisor during my PhD, Professor Alejandro Garcia. And of course, you are invited to see the poster, and comments and suggestions are welcome.
Hello everyone, I am Devasis Hazarika. I am originally from India, but I am studying in the Universidad de Atacama, Copiapó. I am a PhD student and I am working with Professor Carlos Lopez, he's here. So I have a poster which is titled as Variables in S+, Period Luminosity Relations of Classical CFITs in 12 bands. So S+ is a ongoing Southern Photometric Local Universe Survey which aims to observe the Southern Hemisphere sky in 12 bands for the first time, which have 5 SDSS-like broad bands and 7 narrow bands. And the speciality of this survey is that the narrow band photometric filters are present exactly on some special wavelength bands, which mimics the things like calcium which are the calcium triplet or H alpha or like this. So we can think the whole data set as a very, very, very low resolution spectra, but it is a photometric data. So we derived the period luminosity relations from the single epoch data of the CFITs, classical CFITs, both in fundamental mode and first Overton mode for these 12 bands, and for the first time in 7 narrow bands. And we were able to disentangle the effect of the relative distance modulus as well as the relative reddening for each and every individual CFITs. And as a byproduct of that, we constructed the reddening map of SMC and LMC. So that's all from my side. Thank you.
Hello everyone, good evening. My name is Sergio. I'm from Colombia, but I'm doing my PhD in Universidad Nacional Autónoma de Mexico, campus Ensenada. You're very invited to go there, very lovely place, Ensenada. And I'm the third year of my PhD, so I'm doing a kinematical analysis of young stellar cluster in the Orion region, the Orion star forming region, using data from Gaia DR3 and also using a clustering algorithm called HDV-scan that also my colleague mentioned here. So the idea is to detect the clusters in Orion using this astrometric data in order to determine what is going to be the future evolution of these clusters. So if we combine astrometry with radial velocity from spectroscopic surveys such as Apogee and Gala, we can get the 6D phase space. It means positions and velocity. And with this 6D phase space, we want to know what is the future of these clusters. The results of the clustering algorithm allowed us to get a total amount of 34 clusters in Orion, which is the highest amount that has been detected in the literature. 4 of them are new discoveries, and we are right now trying to analyze about these new 4 clusters. And we hope that some of these clusters are having close encounters in the future. It means that they will approach to each other, and perhaps they will have an exchange of energy. And the second part of my PhD thesis will be to do n-body simulations in order to see what is going to happen with this cluster. Are they going to exchange energy? Are they going to merge? Or perhaps they will pass by, they don't see each other in the future. Using the framework called AMUSE, which is a very famous package just to do n-body simulations. And my poster is in the middle size, the first one in the middle size. And if you want more details about my project, my advisor, Jesus Hernandez, will give his presentation tomorrow at 12:30, and you are very invited to that, to see it. Thank you.
Hello everyone, my name is Lubin Cano. I just graduated from my Bachelor in Physics from Bolivia. Well, my poster is about my bachelor thesis that I worked with Giselle Ortiz from INAOE in Mexico. And we studied the water master emissions using radio astronomy. And we focus on two young stellar objects to study more about how is the kinematics and the behavior of these water masters around the disk and around the jet. So it's not a lot about astrometry, but we are working mostly with processing a lot of data, and we are processing mostly using different models to get to know where is these water masters emissions from, because there is previous studies for high mass stars, but we are focusing on low star masses. So yeah, if you are interested in radio astronomy, I'm using data from the BLBA, the Very Long Baseline Array. So yeah, you can go to my poster to check how's it work done. Thank you.
Okay, good evening, everyone. My name is Adriana Vázquez Barrios. Well, first of all, thank you for accepting me here in Adela. I am very glad to be here with all of you. It's an honor to me. Well, I postulate as an undergraduate student of physics, but a few weeks ago I defended my thesis, which was advised by the Professor Laurent Loinard. And the title of my thesis and my poster, which I bring it here, is a search for nervy stars. Sorry, I am thinking in Spanish. So it was a search for nervy stars in the radio frequencies. And what I did was a cross-match between the Gaia data release tree and the very large array sky survey in order to find positional matches between these two catalogs. And I found around 91 coincidences, 91 stars within 50 parsecs. And I'm glad to announce the first detection of variables F8, and of course there are more interesting matches that I found, and I will be very glad if you come to my poster and read it. Thank you.
Hello everyone, my name is João Gardim from Universidade Federal de Minas Gerais, Brazil. And my poster is a preliminary result of high photometry data taken in the context of the Vizcaya survey in the outskirts of the Magellanic Clouds. So we first started with completeness analysis, which was a method that we developed. And instead of adding stars to the images, we added artificial stars to the catalogs, and then estimated the completeness. Then we determined the structural parameters using the King analytical profile. And after that, we are using a family of lower isothermal models to determine the dynamical properties of these clusters. And we can find out the dynamic evolution of these clusters. We started with a preliminary sample of 5 clusters in the Large Magellanic Cloud, but we have observed already a ring around the Large Magellanic Cloud with more than 80 clusters, and we will apply our methodology to these clusters in the future. And that's all. I hope you will see my poster there. I'll be there to answer any doubts. Thank you.
So you just saw how students outperformed most of the speakers here. They did it right on time and even faster. So let us thank them all again, please. I'd like to know how many of the people presenting posters are still to come here, just I need to have a rough number. So you want to do it now or better for tomorrow? Tomorrow. Okay. So, well, thank you for this first day in Adela. Have a deserved rest. We have another announcement, so please, Felicita.
My name is Felicita Arias. I don't have a poster.
But this is the time for announcements.
This is the time for announcement. I don't, yes? Okay. Okay. So, I don't know if speaking in English or in Spanish, but I prefer English for this issue. Maybe you know an editor. It is an open access editor, MDPI. So MDPI invited me a little bit more than 1 year ago to be editor-in-chief of a new journal. The name of the journal is Time and Space. You have the flyers on the tables. So the idea of time and space, if you read herein, is to cover all aspects of time and space physics. So what MDPI is proposing is to publish either individual papers or to propose special issues. So people aiming to work on a special issue, on a topic, can make a proposal. We will find an editor in the house and a guest editor for the special issue, or just individual papers. There are many, many journals in time and space, and for astronomy there are two. One which is Universe, and the other which is time and space. So I encourage you to present your research in time and space. It is open access, but charges are to be paid for publishing. Editors, we have the possibility of waiving, in some cases, the cost of a publication. So if it is justified and we think that it's an important paper, an important contribution, we can waive. We have a number of papers we can waive per year. So I encourage you to bring your papers to Time and Space, and you can contact me. And if you have interest in coming to our journal, of course, we can have a discussion on that. Thank you.
Well, I think we are done for today, so good night and see you tomorrow. Let's see for a moment just the program for tomorrow, Tuesday. So breakfast at 8 a.m., please be on time, 1 hour for breakfast, then short announcement, if any, and then talks. So have a good night.